Hey, geometry students. In this lesson, we're going to be talking about triangle similarity. Now, I've introduced a lot of other lessons that we're going to be talking about triangle congruence. And we learned about things like side angle side congruence, angle side angle congruence, angle angle side congruence. And then we learned a bunch of congruence theorems specific to right triangles, hypotenuse leg, leg leg, hypotenuse angle, leg angle. In this lesson, we're going to talk about triangle similarity, not congruence. Okay, this is going to be when we have two triangles that do not have the same side lengths, at least not necessarily. They could, but they probably don't. So they don't necessarily have the same side lengths, but their side lengths are in proportion to each other. Now, obviously, not all triangles have side lengths in proportion to each other, but the ones that do, we call similar triangles. Okay, that's the definition of similar triangles. Similar triangles have side lengths that are in proportion to each other. Similar polygons are polygons that have side lengths that are in proportion to each other. Another thing about similar triangles, the angles of similar triangles are congruent, just like the corresponding angles of similar polygons are congruent. That we learned in a previous lesson. Now, how can we prove that triangles are similar? Well, in this lesson, we're going to learn a few postulates and theorems that can prove triangles are similar. And the first is the angle-angle theorem. Postulate. Sorry, this is a postulate. This is not one that we've proven. This is one that we're just like, well, duh, this is obvious. All right. If two angles of one triangle are congruent to two angles of another triangle, the triangles are similar. Wait a second, you might ask. Shouldn't there be three angles required to prove prove similarity? I mean, wouldn't all three angles have to be the same? Yes, but think about it. If two angles of a triangle are similar to two angles of another triangle, could the third angle possibly be any different? We've backed that third angle into a corner because all three have to add up to 180 degrees. So if two angles are the same, the third one also has to be the same. Therefore, we only have to prove that two of them are the same because the third one is obviously automatically the same. And that's the angle-angle similarity postulate. Now we come to a theorem, the side-side-side theorem. This one can be proven. If the lengths of the sides of a triangle are not congruent but proportional to the lengths of the sides of another triangle, then the triangles are similar. Now you may remember there is a side-side-side congruence theorem as well. If three sides of a triangle are congruent, the triangles are congruent. This is saying if the three sides are not congruent, if the three sides are proportional to the lengths of the sides of another triangle, then the triangles are similar. You have to prove that about all three sides, though. So the first one's really a bargain postulate because we only have to prove about two angles. This one we have to prove about three different sides. And then the last one, notice there are three things. Side angle side theorem says that if two sides of a triangle are proportional to two sides of another triangle, but now listen to this change up here, but the included angles are not proportional but congruent. Now remember, in similar polygons, the sides are proportional but the angles are congruent. Okay, so keep that in mind. If two sides are proportional for two triangles, but the included angles between those two sides have to be the same, they're congruent, then the triangles are similar. All right, and again, we're talking about similar triangles, not congruent triangles. So we have to have proportional sides and the same included angle. Let's take a look at some practice problems here. Letter A, given the two triangles shown, prove that they are similar using the angle-angle similarity postulate. Well, as I look at this, I see that we have some parallel lines and some transversals going on. So here's how I would start. I would start by saying that line AB and CD are parallel to each other. That's a given because it's shown in the figure. And line AC is a transversal, another given shown in the figure. Okay? Then what I would say is that BAC and ACD are alternate interior angles, and because of an old theorem, Theorem 10.1, the alternate interior angles theorem, I know that alternate interior angles are congruent. I'm going to do the same thing. So I've got this angle here and this angle here. I can do the same thing for this angle here in this triangle and this angle here. And if I prove that two angles are congruent, that means that the two triangles are similar. So let's do this. Line BC and AD are parallel with AC as a transversal. BCA and CAD are alternate interior angles by that definition, and therefore they're congruent. And voila, I've proven that two angles in these triangles are congruent. So I can just say triangles ABC and CDA are similar by postulate 21, the angle triangle similarity postulate. Letter B. Given the two triangles shown, use side similarity to prove that they are similar. Okay, so for side similarity, all I have to do is prove that the sides are proportional. I see that I have two sides that are not decimals, have no decimals involved. That's a 5 and an 8. So I'm going to say that there's a 5 to 8 ratio between the similarity ratio between this triangle, the smaller one, and the larger one. So that means if I let's see, so for every if I say there's 5 to 8, that means that every side of this triangle should be 5/8 of the larger triangle. What's 5/8 of 8? 5. Does that make sense? So what's 25.6 times 5/8? All I have to do is do the math. 25.6 times 5/8. That gives me 16. 25.6 times 5/8 is 16. If I were proving this in a two-column proof, what I would do is I would just write out the math. 25.6 times 5/8 equals 16. And I would just say multiplication. 14.4 times 5/8. 14.4 times 5/8 is 9. And that's what it had to be. So because 8 times 5/8 is 5, 25.6 times 5/8 is 16, and 14.4 times 5/8 is 9, the three sides of these triangles are proportional. Therefore, they are similar according to the SSS similarity theorem, Theorem 46.1. Let's look at C. Given the two triangles shown, use SAS similarity to prove that they are similar. Find the value of x. Okay, so again, I'm not going to put out the whole two-column proof for this, but I'm going to lay it out for you. We're going to do the same thing that we just did. And another way to do it is just to divide the sides and see if they're all in ratio. So what I would do is say 10 divided by 5 equals 2. That's division. 8 divided by 4 equals 2. Also division. The ratio of EC to BC equals the ratio of DC to AC. Okay, that's powerful because I just proved that two sides have the same similarity ratio. Two sides are proportional. I would say that they're proportional. And then I can say that ACB and ECD are vertical angles by the definition of vertical angles. Therefore, ACB and ECD are congruent according to the vertical angles theorem. And because I'm saying that, I've proven that this side is proportional to this side is proportional to this side, and the included angles are congruent. Therefore, the two triangles are similar according to the side angle side similarity theorem. Now, just one more step. I need to find the value of x. Well, that shouldn't be too hard because that means that this is in ratio to the rest of the sides. So I know that 13 divided by 2x plus 3 has to equal 2 because the ratio of the sides always equals 2 in this triangle. So I'm going to multiply both sides by 2x plus 3. I get 13 equals 2 times 2x plus 3. That simplifies out. 13 equals 4x plus 6 if I distribute. I'm going to subtract 6 from both sides. 7 equals 4x, and then x equals equals 7 over 4. And let's just make sure I got that right because I've got a fractional answer there. 1.75 is the same as 1 and 3/4, which is 7 over 4. So we did get that one correct. First of all, proving side angle side similarity, and then that x equals 7 over 4. All right, and lastly, Laura wants to find out how tall a tree is. She notices that the tree makes a shadow on the ground. The top of the shadow of the tree house is 25 feet away from the base of the tree. Laura is 5 feet 8 inches tall, so we're going to change it to feet right away. 5.67 inches tall. And she casts a shadow that is 6 feet 2 inches long. How tall is the tree to the nearest foot? All right, so we've got some figuring to do here. We have two triangles. The shadow that Laura makes and the shadow that the treehouse makes. Let's start by drawing those two shadows or those two situations, okay? So the tree is here. This is the height of the tree. This is its shadow along the ground. And then Laura is going to have a similar thing going on. Now, because the sun is shining at the same angle, we know that this angle here is going to be congruent to this angle here because the sunlight's coming in parallel. So this angle and this angle are similar, are congruent to each other. Also, this is going to be a right angle because the tree is standing upright and Laura's standing upright. So I've got angle similarity going on. And that's what I'm going to use. I know these two triangles are similar. So the top of the shadow of a treehouse is 25 feet away from the base. That means that I have a 25-foot long shadow here. Okay. And then the top of, let's see, Laura is casting a shadow 6 feet and 2 inches long. Let's just change that. And I know how to change that. So that's going to be 6 and 1/6 feet. We're going to leave that in fractional form to keep our decimals exact for right now. 2/12 is the same as 1/6. Her height is 5 feet 8 inches. So we're going to say that she is 5 feet and 8 inches is going to be, let's see, that's 8/12. So 2/3 of a foot, 5 and 2/3 feet. Now, if these are proportional, the proportion we're working with here is let's see, and this is going to be our y value. We're going to make this the variable y. So we'll say 5 and 2/3 compared to y equals 6 and 1/6 compared to 25. Cross multiply, we get 25 times 5 and 2/3 equals 6. There we go. All right, let's go ahead and do that. So 25. So I have 25 times 5 and 2/3, and I'm going to divide that by 6 and 1/6. That's going to give me 22.97. So y, the tree, must be 23 feet tall. And let's just make sure we got that right. 23 feet tall. So I set up my proportions. I drew my picture, set up my proportions, solved, and found that the tree was 23 feet tall. Now you know how to work these problems. You should be able to work the practice problems for next time.